Hello everyone, welcome to this video. So in this video we're going to talk about uniform distribution. So as we have already saw that in discrete distributions part, uniform distributions is basically where the probability remains a constant, right? So let me just give the heading. It's uniform distribution, and we're going to find out all the properties about it. So first of all, let me write the statement. So if x is a random variable which follows an uniform distribution on the closed interval a comma b, where a and b are real numbers and a is less than b, the PDF is given by this: f of x is equals to 1 by b minus a for all a less than x less than b. Okay, so this is basically the PDF of uniform distribution. Now, to check if it's a PDF, it is enough to see that since a is less than b, b minus a is greater than 0, which also implies 1 by b minus a is greater than 0. This means fx of x is greater than 0. So the non-negativity part is completed. Now integral over all real numbers fx of x dx should be equal to, now see, since the region of integration is basically in the closed interval a to b, we understand that this is basically a to b f of x dx, and we know the PDF, which is basically 1 by b minus a dx. So this will give us 1 by b minus a is a constant, so we are basically integrating a to b dx. Now a to b dx is basically the length of the interval, which is b minus a. Since b minus a is positive and not 0 ever, it becomes 1. Therefore the total probability is 1, therefore it's a PDF. Therefore it is a PDF. Now the CDF. So once we are done with the PDF, we move on to the next thing, which is the CDF. As I have already told you, it's called the cumulative distribution function, and it is defined as probability of x less than equals to x, that is capital F for denoting the CDF, which is basically probability of x less than equals to x. And whenever you want to find the probability between any two ranges, you just need to integrate. Now we know the lower range is a and the upper range is given as a variable x, and we are integrating 1 by b minus a dx. This will just give you x minus a by b minus a, which is the answer for the CDF, right? And we always know a less than x less than b. So the CDF and the PDF are pretty simple for uniform distribution, and uniform distributions are mostly used when we are trying to figure out some distribution which remains constant or which has a constant probability value over a certain period of time, or maybe over a certain period of days, maybe over some certain book intervals. So it can be anything, but you need to know when to model an uniform distribution. So let's say a car goes and the speed remains uniform, so its speed can be modeled as an uniform distribution, and the probabilities can be assigned accordingly, according to whatever event we are calculating at. So that becomes the CDF. And now let us talk about its moments. So let us first calculate the first moment. So the first moment of the mean is given by expectation of x equals to a to b x by b minus a dx, and this would give us 1 by b minus a to b x dx. Now understand this fact that a to b x dx can be evaluated very simply by using the antiderivative of x, which is x square by 2, which means it will become x square by 2 from a to b. It will thus become 1 by b minus a into b square by 2 minus a square by 2, right? Now simplifying this is not very hard because it is just b square by n s a square by 2 into b minus a, and this becomes b plus a into b minus a divided by 2 times b minus a, and this becomes b plus a by 2. So you see the mean value for a uniform distribution, as you would expect, and you understand why we call it an average as well, is basically the average length of the interval, right? So for example, if you had an interval length 3 to 5, the mean of this interval would be 4, which lies exactly in between 3 and 5, because 3 plus 5 by 2 is 4. So for a uniform distribution, this remains as one would expect it to be. Now the second moment, we are calculating the second moment in order to attempt to find the variance of the uniform distribution. For that we need the second moment. So the second moment is basically a to b x square by b minus a dx, and the antiderivative for x square is x cube by 3. This becomes 1 by b minus a whole into b cube by 3 minus a cube by 3. So therefore it becomes that b cube minus a cube by 3 times b minus a. That is how things simplify. Now we can use the cubic formula to find out. It is basically equals to b minus a into b square plus ab plus a square whole divided by 3 into b minus a, and we cancel off everything. The answer is a square plus ab plus b square by 3. So we got the second moment and we got the first moment. Now we can have a look at how the variance would look. Therefore the variance is var of x equals to e of x square minus e of x whole squared, and this would give you minus a plus b by 2 whole square. So we are going to simplify this thing and find out what the variance looks like. So first I'm going to do it. You can follow the steps as I'm going to write them slowly and clearly. So I hope you can understand the manipulations because it's just basic algebra. So this becomes, when you do the LCM, it becomes 4a square plus 4ab plus 4b square minus 3a square minus 6ab minus 3b square. So we group the like terms together, and after simplification we find that this is equals to a square minus 2ab plus b square by 12, and the above is just the formula for a minus b whole square. But since we know that b is greater than a, we can rather write it as b minus a whole square by 12, which is the variance for the uniform distribution X, which follows uniform distribution in A comma B. Now the standard deviation is just the square root, so SD of X, which is denoted by sigma X, is just root over of variance of X, and it is given by root over of B minus A whole square by 12, which is basically B minus A, and 12 is 4 into 3, which is 2 root 3. So this is the required variance, this is the required standard deviation for uniform distribution. Now we have completed the usual topics which we find first. Now it's time to find the higher moments. So the nth moment is given by e of x to the power n equals to a to b x to the power n by b minus a dx. And since you know the antiderivative for x to the power n is just x to the power n plus 1 by n plus 1, and this gives us 1 by b minus a, and x to the power n plus 1 by n plus 1 a to b, and this would give you b to the power n plus 1 minus a to the power n plus 1 by n plus 1 whole into b minus a. This is the expression which is for the nth moment of the uniform distribution. And so things are pretty simple here because of this fact. Now what we can do is we can find the MGF and the CF as well. So the MGF will look something like this. So it is given by mx of t as usual, which is expectation of e to the power tx, and this is equal to integral of real numbers e to the power tx. The PDF is 1 by b minus a dx. Now since the integration region is just a to b, we see that this is equals to a to b e to the power tx by b minus a dx, and this would give you e to the power tb minus e to the power ta by t into b minus a. This is the MGF for the distribution, and you can also expand it in forms of infinite series by using e to the power tb's expansion and e to the power ta's expansion and subtracting them together, and you can find out it in terms of powers of t, but that is not required right now because we have already found out higher moments in a separate form. So that again this will be the form. So what remains to find is the CF. So it is given by phi x of t, which is expectation of e to the power itx, and this is given by a to b e to the power itx fxx dx, a to b e to the power itx by b minus a dx, and similarly it becomes 1 by b minus a into e to the power itx by it from a to b. So the final answer is the MGF is e to the power itb minus e to the power ita divided by I t into b minus a. This is the CF, or the characteristic function for the uniform distribution. So this sums it all for the uniform distribution. It was quite an easy one, and so we could cover it in a single session. So that would be it for this video, and for the next video we'll try out the gamma distribution. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also, you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.